Hello and welcome to the third lecture of this short course called Behavioral Theory of Systems with a view towards data-driven control. So far we have looked at the basic concept called the behavior of a system, and we have argued that this is perhaps the most fundamental method, the most fundamental way to describe a system, right? Just to brush up our memory, behavior B of a system is a subset of all the possibilities called the universum. This is the behavior of the system. Okay, this is the universum. So universum is all possibilities. Then we look at the system and we apply the laws of physics that restricts the possibilities to a subset, and that's the behavior. The kind of behavior, the kind of system that we are interested in throughout this course are the so-called dynamical systems, where these the variables are functions of time. Okay, dynamical systems, functions of time. So there it turns out that the behavior will always be a subset of this set of all possible trajectories, all possible functions, right. So this T is called the indexing set, W is called the signal space, and B as usual is the behavior, right. We have seen a couple of examples of behaviors, namely circuit behaviors of dynamical systems, namely electrical circuit and the planetary motion. Okay. Let us look at another example of such a dynamical system, something that all of us are very familiar with. If we have a system like this where there is this transfer function and you give input, the input Laplace transform, the output Laplace transform, right. If you look at the corresponding time functions ut and yt and look at all these two tuples which are possible, that is with 0 initial conditions, the ones that are related with each other through this, you form this, the corresponding Laplace transforms satisfy this relation. That itself is the behavior of this system described by this transfer function. Likewise, if you look at a state space equation for a system, remember x dot equals ax plus bu, y equals cx plus du, right, where A is a matrix of size n cross n, B is a matrix of size n cross m, C is a matrix of size P cross n, and D is a matrix of size P cross m. X T is an element of Rn, ut is an element of Rm, and yt is an element of Rp, right. Then one can actually define B full in this case is the collection of all x, y and u which are functions of time. It maps from R to the power n cross R to the power p cross R to the power m, such that this equation, such that 1 is satisfied. Yeah, this is the full behavior, and the behavior in this case will turn out to be the collection of all y and u such that there exists x, which is a function from R to Rn, such that x, y, u is a part of the full behavior. You see, a latent variable description for this system. This is something that we are, those of you who have done a little bit of control theory, you will all be familiar with such a description, but this is new, that this can be viewed in behavioral theory terms, how this the state space equations give rise to a behavior. Okay. Now you see, then I mean, this begs the question that why this new description? It looks like same thing, a little same thing in a fancy way. Yeah. So then, what's the point really of writing it this way? You see, there are many benefits of writing equations in terms of behaviors. We don't want to go into the debate of why this is better than the state space description or the transfer function kind of descriptions. Yeah. Rather, what we would like to do is, with this description, yeah, we will see that how it becomes handy when we try to ask questions which are fundamental to say data-driven control. For example, just ask yourselves this question: that okay, suppose this is your time axis, yeah. Suppose discrete t, this is a discrete time axis, and suppose we are starting with 0. So the non-negative integers are my non-negative integers, the set of non-negative integers, that's my indexing set, like this. And I have noticed the value of a particular trajectory, say w hat at 0, w hat at 1, w hat at 2, w hat let us say at 3, w hat at 4, w hat at 5, and w hat at 6. These are the various things I've noticed. Perhaps I can notice it for all time, or I can notice it for a finite period of time as well. So this is the information that I have, the data that I have of this. Okay. So then, in that case, if I notice by w hat this particular trajectory, then whatever behavior it was, whatever system it was coming from, the system's behavior must contain this trajectory, right? Just by the definition of the behavior. Now, suppose, remember what we said about linearity and shift invariance of a behavior of a system. Suppose I assume that the system is shift invariant and the system is linear. Then from this information that w hat is in B, I can immediately conclude, I can immediately infer that w hat shifted by 1 unit, one left shift by 1 unit, that must also be a part of the behavior. What does that mean? That immediately means that w hat 1, w hat 2, w hat 3, a trajectory starting from w hat and going on like this must also be a part of the behavior. Yeah. Not just that, now that sigma w hat is a part of the behavior, sigma square w hat must also be a part of the behavior, sigma cube must also be a part of the behavior. So indeed, what we are witnessing here is that the moment I say w hat 0, w hat 1, w hat 2 being a part of the behavior means w hat 1, w hat 2, w hat 3 must also be a part of the behavior. W hat 2, w hat 3, w hat 4 must also be a part of the behavior, and so on. Okay? Now, not just that, you see, because I have assumed my system is linear, any linear combination of these guys, will also be a part of the behavior. Right? In other words, anything in the row span of this matrix, whatever, let me call it a capital W hat matrix, must be a part of the behavior. So, the row span of this guy is actually contained in the behavior, right. This is this like the smallest behavior that I can, smallest subspace that I can generate from this W with the information that from W hat with the information that my system is linear and shift invariant. This is an immensely important fact, and which will become which will become very important for us when we concentrate more on data driven control. Okay? So, you see the behavioral description tells me that I can start with just the basic rudimentary of of a trajectory, the rudimentary fact that this trajectory is a part of the behavior, and then from there by using the property that my system is linear and shift invariant, I can get all so many new trajectories in the behavior. Now, later on we will ask this question, that is it possible to identify the system from this information, and when is it possible, when is it not, right. Okay. So, now moving on, so we asked this question that what kind of descriptions can we have for behavior. We have seen that the examples that we have concocted, we have looked at examples where there are equations which describe a behavior. We have also seen laws which describe a behavior. Okay. The kind of behaviors that we will be concentrating mostly on this, in this course, the kind of system that we will be concentrating the most are the ones that are described by linear differential equations with constant coefficients. One might ask that why only these systems? The quick answer is that because they are the simplest to analyze. Is it that the kind of things that we are going to do are restricted only to this kind of systems, only to this kind of equations? Well, not exactly. You can do a lot more with other kinds of equations like nonlinear equations, time varying equations, and so on. But because it is a short course, we are going to do only the basics. So, therefore, we are going to restrict ourselves only to equations, to differential equations which are constant coefficients, which have constant coefficients. However, we are going to look at not just differential equations, but we are also going to look at difference equations, right? And we will see that the behavioral theory, this approach, the behavioral approach to deal with dynamical systems allows us to handle these two different kinds of systems, namely difference equations for discrete systems and differential equations for continuous systems. We can deal with these two things simultaneously. Simultaneously in the sense that with almost no difference, small slight differences will be there, but almost in a unifying manner we can describe these two different kinds of systems, dynamical systems. Okay. One very important thing about differential equations and difference equations is that the distinguishing factor about these equations happens to be the fact that these descriptions are local. You see, these descriptions are local. Why do I say that? Because, okay, let us think of a typical differential equation. Let us look at a system to get our differential equation. This is a system that I am sure all of you have seen before in one form or the other. This is a spring mass dashpot system where there is a mass that is being pulled by some force F. There is motion of this guy, which is our main function, and this spring has a constant K, this dashpot has a constant D, and we know that if you apply Newton's laws to it, yeah, and then draw the free body diagram. The free body diagram says that there is a force experienced by this guy because of the spring, which is k times x. It also experiences a force due to this dash part, which is d times x dot, yeah, viscous friction, which causes this force to be there. There is this pseudo force due to the motion, which is given by m times x double dot, where x double dot is the acceleration, the double derivative, the second derivative of x. Okay, and here is this. Sorry, I have drawn it wrongly. Yeah, the motion is in this direction x. So therefore, the pseudo force will be in this direction. This is the force Ft. So the differential equation that this system satisfies, which comes from the force balance equation applied to this free body diagram, is m d square x dt square plus d times dx dt plus k times x equals f. That is the differential equation. What is the behavior? The behavior, of course, is the collection of all x and f functions of time which satisfies this equation. Okay. This is the example of a differential equation with constant coefficients. All right. Now, if you have a more complicated structure which has multiple springs, multiple masses connected through some interconnection, what will happen in that case is that you will have system of such differential equations, right? So there could be x, which can be a function which can be a vector, xt can be a vector of size q, right? F can be a vector, the force Ft can be a vector of size m, right? And in that case, one might end up getting equations which are like m times d square x dt square plus d times dx dt plus k times x, which is equal to f. Looks like this, but the catch is that m can then be a matrix of size m cross q. D can also be a matrix of size m cross q, and k can be a matrix of size m cross q, like that. Yeah, this actually is a system of m equations involving m plus q number of variables. Okay. Now, so what we expect in this situation? Yeah, this is something which is very special because it's a quadratic differential equation. In general, it could be a higher order differential equation, right? So what we expect in this situation? So what happens is that, okay, I'm sure you have seen this before. This is just perhaps a recap for you, just a recall for you. But remember that all we are doing is that we are looking at this d dt kind of an operator. Yeah, this d dt operator, this acts on one's differentiable functions, but because we will allow arbitrary powers of this differential operator, it is best to assume functions which are infinitely often differentiable, called C infinity. This is the symbol that is used for denoting functions which are infinitely differentiable or smooth functions. So C infinity functions to C infinity functions, the smooth functions is mapped to a smooth function by this d dt operator, and So, what does this do? It takes a trajectory w and maps it to its derivative, right. Likewise, you can have this operator which maps a trajectory to its second derivative. In general, we can have dk dtk, the kth derivative operator. Okay. Now, one can also have a combination of these operators, namely one can have something like ak to the power dk dtk plus dot 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 a1 d dt plus a0 acting on w. What does this produce? This produces ak dk w dtk dot 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 a1 dw dt plus a0 times w. So, you see this also is a legitimate operator from C infinity to itself. What is such a thing? Such a thing is what is known as a polynomial differential operator. Okay. What is this? So, polynomial differential operator is a polynomial in the variable d dt. This is a typical polynomial differential operator. Okay. This often will be written as a polynomial a d dt. That is the notation that we are going to use to denote this polynomial. Okay. As you can see, it is tedious to write d dt all the time. So, we will replace, because we are just going to treat this as a polynomial. Yeah, we are not going to. So, at least this, when I write this thing, I could have replaced this by anything. Yeah, I am not using that the fact that it is a differential operator. Yeah, it is differentiating. As far as these differential operators are concerned, their products and so on. Yeah, I do not need them to be d dt. So, I will use this placeholder xi to denote that it is the derivative operator. So, I am going to write this as a xi. And the notation that we are going to use for the set of all polynomials with constant real coefficients is this, r and xi within square brackets. This is the set of all polynomials, the set of all polynomials in xi with coefficients from a set of real numbers. Okay. Therefore, a polynomial differential operator, which looks like this, acts on a trajectory w equal to 0, gives me an ordinary differential equation. Right. Likewise, if we have w1 w up to wq, if that is my w, this is my w, q tuple. You see, I can also make a polynomial differential operator a1 act on w1, a polynomial differential operator a2 act on w2, and a polynomial differential operator aq acting on wq. So, a row vector of polynomial differential operators can act on a column vector of trajectories to produce a1 xi w1 plus dot 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 aq xi wq, and that equal to 0 can be one equation. Likewise, I can have several such equations. So, I can have R11 xi R 1 2 psi dot 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 R1 q xi R21 xi R22 xi dot 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 R2q xi dot 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 RG1 xi RG2 xi dot 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 RGQ xi. That's a matrix of polynomials that can act on a vector of trajectories and can produce a 0. That's a system of ordinary differential equations with constant coefficients. Okay? I can use this shorthand notation of R xi to denote this matrix, which is now a G cross Q size. Okay, let me not use that, I'll try it this way. R xi G cross Q. So, it is a G cross Q sized matrix where the coefficients are coming from polynomials with constant real coefficients, right? And my systems equations, I mean the differential equations are just R d dt w equal to 0. So, in that case I can describe my behavior as the collection of all w which are C infinity functions from R to RQ, yeah, RQ, the Q tuples of C infinity functions which satisfy the differential equation R d dt w equal to 0. This is my behavior. This is a behavior that is described by a linear ordinary differential equation with constant coefficients. Yeah, linear ordinary differential equation with constant coefficients. So, these are the kind of systems that we are going to concentrate on mostly in this course. Now, this is for continuous systems. What you do for discrete systems is something quite similar to it. In fact, for discrete systems, you see, like we have the differential operator d dt, for discrete systems we have this shift operator sigma. What does it do? Sigma acts on a sequence and produces another sequence. What is its defining property? When sigma acts on w, the value that it takes at a point, let us say k, is w at k plus 1. This is the left shift. Obviously, sigma inverse will be the right shift. Yeah, so left shift and right shift both are legitimate operators. You can have obviously a shift that shifts j times on the left, or a shift that shifts j times on the right. You can also have linear combinations of these. So, one can have something like say a n sigma to the power minus n plus a n minus 1 sigma to the power minus n plus 1 plus dot dot dot. Okay. And then we have a0, and then we have a1 sigma plus dot 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 a p sigma to the power p, positive power p. That is a standard so called LoRa polynomial. In the shifts, yeah, we denote this by a sigma, and a difference equation can be written as a sigma w equal to 0. And now you can do exactly the same set of, you go through the same set of arguments that we did before, and you can come up with a matrix R sigma, which is now a matrix of LoRa polynomials, sigma inverse, of size G cross Q, such that R sigma W is equal to 0. And the behavior will be the collection of all those W's which are sequences, Q tuples indexed by Z, which satisfies this equation. Yeah, this ordinary difference equations with constant real coefficients. Right. So, in both these cases what we have is that the behavior is given by the zero set of these polynomial difference or differential operators. So, because it is the zero set, we write that the behavior is nothing but the kernel of this operator, either R psi or for continuous systems, or of R sigma for discrete systems. R psi for the continuous case is a polynomial matrix of size G cross Q. R sigma on the other hand is a polynomial matrix with LoRa polynomial entries of size G cross Q. That is the kernel representation. This is called a kernel representation of the behavior. Right. So, you see that is how we represent differential equations with differential or difference equations, linear with constant coefficients. Right. We will see that these behaviors are in fact linear and shift invariant, the ones that we want. And now we will ask the question that given a behavior, given a system of equations, can different systems of equations give rise to the same behavior? And if they do, when do they do that? How can we figure out whether two systems of equations give rise to the same behavior or not? And we will see that ideas from commutative algebra actually gives answer to this question, right? That and many more is what we will see in the next few lectures. Till then, take care of yourselves. Bye.